Hello everyone and welcome to our calculus notes for section 6.2. Today we're talking about volume and specifically the disk method. So to start our conversation today, we want to talk about something called solids of revolution. And calculus is pretty amazing because it can help us find volumes of solids you didn't learn about in geometry. So take this coffee cup for example. So you can see that by keeping his fingers here in a straight line, okay, but revolving the clay around on this table, he was actually able to create a physical solid, and that's what we're talking about when we mean solids of revolution. So by rotating a plane region as bounded by a set of functions around a line, which would be an axis of revolution, you create a solid of revolution. So I'm going to click the link below for an illustration, and if you're on a computer you can also do this and try it out for yourself. Okay, so here we have a function right on top. It's kind of curved, and then we have another function on the bottom. And in our last lesson we learned how to find the area between these two curves. Now what we're going to do is we're going to rotate this region around the line y equals -1. You can see that here in red. And this is our three-dimensional model that we can see. And if we take this region and we rotate it, you can see that we are indeed creating a solid. So if we rotate this all the way around 360 degrees, then we would get this solid right here. Okay, so what we're going to be dealing with today is trying to find the volume of this solid right here based on this region. Now, one way to find the volume of a rotational solid is by slicing the solid into disks, which are also cylinders, of increasingly smaller widths and adding up their volumes. Okay, so we'll take a look at the demonstration here. Okay, so here we are looking at the function the square root of x, and you can see if we rotated this around the x-axis we would get this solid right here. Okay, and what the disk method is going to do is as we increase the number of disks, okay, so we could fit maybe one disk in here by cutting this into two regions. This disk would be nothing, and then this disk would be a little bit bigger. This would give us an approximation. So you can see our true volume is 25.1327, and the approximation here, because we can find the volume of a disk using geometrical formula, is 12.566. Now if we increase this, now we have three disks. The first disk is 0, and we get a very crude approximation again as well. But if we increase the number of regions, okay, and shrink this interval or the height of these cylinders, you can see that the approximation is going to get closer and closer to the actual value of the volume. And this is really what we've been doing all along in calculus. So you can see here lots of disks, our approximation is getting very closer. And if we increase this all the way up to 30 disks, you can see that our solid looks very much the same. You can see just these little steps right here, and our approximation's getting even closer. So I just want to play this for you so you can view the approximations happening. Okay, so what we're going to be doing today is learning how to make these disks, make their heights shrink to 0 and increase the number of disks to infinity, and then we're going to get a pretty good approximation for our volume. And the way we're going to do that is by using integration. Okay, so we can use the volume of a disk, which is pi r squared times the width or the height of the disk, to find the volume of each cross-section and express the volume of the entire solid in terms of a definite integral. So let's take a look at this link to see how we're going to do this. Okay, so here you can see our function, and then you can see the solid that's generated by revolving this around the x-axis. Okay, and we're going from our interval from A to B, and here you can see there's one disk here at a value of x. And you can see that I can slide that x to kind of wherever it goes. And the cross section at x is going to be in the shape of a circle. And you can see that the circle is going to have a radius right here. And that radius is actually going to be f of x, or the height of the function at that given x. So you can see that the radius is going to change based on what x is. So the radius is always going to be f of x. Now if we wanted to find the area of this circle, remember area is pi times radius squared, and our radius is now f of x. So the area of this circle is going to be pi f of x squared. And you can see the cross sections here. Now if we wanted to find volume, okay, the volume of the solid now is going to be the sum of all of these little disks from A to B. And remember, our definite integral is basically finding that sum. So it's the area of the circle, which is pi times the radius squared, or pi f of x squared, times the height of the circle, which we're going to let equal to dx, which remember goes down to 0. So all in all, the volume of the solid is going to be the definite integral from A to B of pi times f of x squared dx. Okay, so let's just make sure we jot this down, that our radius of our cross section is right here, and the radius is going to equal f of x, and the area of the circle then is going to be pi times the radius squared, which was f of x. And so if we want to find then the volume of this entire thing, we're going to take the definite integral from A to B of pi times r squared, which is f of x squared, and then times the width of each of those disks, which is going to be dx. Alright, so let's take a look at a formal definition of our disk method here. And we're going to start with the horizontal axis of revolution. So here you can see our horizontal axis. And let's go ahead and just draw some function here. Kind of like this. And we're going to call this function capital R of x. And we use the letter R because it's going to stand for a radius. And we want to find the volume from A to B. So we'll just call A right here and B right here. And let's go ahead and draw a picture of revolving this around. So what we have to think of is if we took this line and we spun it around this axis in this motion here. Okay, so what we need to do is kind of mirror the function on the other side as best as you can. Okay, And then we think of taking this and revolving it around the axis. And remember, what we're really revolving here is this entire shape right here. Now what's happening here is we're actually taking these rectangles right here and revolving them. Okay? And if we look at this, the height of this rectangle is going to be r of x, and the width of the rectangle is going to be delta x. Okay? So it's important here to note that the radius is going to be r of x, and the width of the rectangle is delta x. And so here is your overall formula of volume is pi times the definite integral from a to b of our radius, r of x, squared dx. So all that happened here was this pi had been on the inside, and we can take it out because it's a constant. So the biggest thing when it comes to a horizontal axis of revolution is that r of x is a function that represents radius in terms of x. Okay, so let's take a look at a vertical axis of revolution. Okay, so we could have a function kind of looks like this, and I'm just going to draw my x-axis in here. Now in this case, if we rotate this area around right here, we would now want to rotate it around the y-axis. Okay, so I always like to draw that rotation figure so I know where I'm going. And so it's going to mirror on the other side. And then we're going to draw in our little discs right here. Okay, give it a little three-dimensional view. And then what we need to do is find that representative rectangle that's getting rotated around. Okay, which would be right here. Now, if we look at this, the radius along here ends up being the value r of y. Okay, and the width of this rectangle is delta y. And our interval here is going to be from C to D. And notice these are going to be y values here. And so the volume formula is very similar. It's just going to be pi times the definite integral from C to D of r of y squared and then dy. Okay, so the big thing when you have a vertical axis of revolution is that r of y is a function where the radius is in terms of y. Alright, so let's take a look at some examples of how this is going to work here. Okay, so it says find the volume of the solid form by revolving the region bounded by the functions around the given line. So here we have f of x equals the square root of sine of x on the interval from 0 to pi, and we want to revolve this about the x-axis. Okay, so here's our x-axis, and we want to revolve it around this axis here. Okay, so this is going to get mirrored on the other side, and then it revolves right here. Okay, we almost have like a little football type of shape, and we want to draw in our representative rectangle. Okay, and the width here is going to be delta x, because it's the width of the x. And then the height of that rectangle is going to be r of x. So we do have the radius is going to be in terms of x, and the width will be delta x. So here, the volume is going to be pi times the definite integral from 0 to pi of the radius, which in this case is just r of x, so it's going to be the square root of sine x squared with respect to x. Okay, so that is our disk method there. And you could type this straight into your calculator, or we can clean it up a little bit. And you can see here sine x, the square root of sine x squared is just going to be sine x. And when you type this in your calculator, we're going to get approximately 6.283. Again, we could find this by hand, but go ahead and use your calculator to get our approximation. Now in calculus it's very strange because these are really cubic units, but for some reason the textbook doesn't stress putting that there. But just realize that this is a volume of revolving this region right here around an axis. Alright, let's try our next example. Here we have the curve y equals x cubed, and we want to also take a look at y equals 1, which is right here, and y equals 8, which is right here, and we want to revolve this about the y-axis, which is right here. So you can see that the region that we're trying to revolve ends up being this one right here. Okay, so we'll mirror this on the other side. And then we will rotate it. About the y-axis. Okay, now what we need to do is find our representative rectangle. And now, when we look at this rectangle, the radius is actually r of y. Okay, and then the width of this rectangle is now going to be delta y. So what we need to do is get our function y equals x cubed and rewrite it in terms of y. So if we wanted to solve for x, we would just take the cube root of both sides. So x equals the cube root of y. And basically, if you're trying to find r of y, that's what we need, an x equals function. So r of y equals the cube root of y. Here, now that we have r of y, we can find our volume. And we get pi times the definite integral. And now it's going to be these y values here. And that was why we had the lines y equals 1 and y equals 8. So this is going to go from 1 to 8. And then our radius is the cube root of y. And then we square it. And then dy. Okay? And then you can use your calculator to find this. And the volume is going to be about 58.434 cubic units. Okay, so that's how we revolve about the x-axis and then also about the y-axis. The only trick with the y-axis is we have to change this into a function of y and then use our limits of integration, which would be our y values. Now in our next two examples, we're going to be revolving around horizontal and vertical lines, but they aren't going to be the actual axis. And so it forces us just to think about our radius a little bit more carefully. So first we have the function 2 minus x squared, and 2 minus x squared, and this is also going to go g of x equals 1. Okay, so here is g of x equals 1. And it turns out 2 minus x squared, if I plug negative 1 in there, negative 1 squared is 1, 2 minus 1 is 1, so I get this point here. If I plug in 0, then I would get 2, and if I plug in positive 1, I also get 1. And so we kind of get this shape, little parabola right there. And now we're revolving this about the line y equals 1, okay, which is right here. So I'm just going to draw that little revolution symbol there. And so this is going to get mirrored in the other side. And so this is going to get mirrored in the other side. And then rotated around. So we'll make this look a little three-dimensional. And so you can see here, we are going to have vertical rectangles because we're revolving around that horizontal line. And the width of the rectangle is going to be dx. And now we need to find the radius of the rectangle, which is rx. Now in this case, rx is not the same thing as f of x, because f of x, remember, would be the entire height from the x-axis up. So there is your f of x. But we don't want the whole thing, we just want this part. And so we have to think we're actually going to be subtracting this amount, which is actually g of x. So r of x, in this case, the radius, is going to be f of x minus g of x. Now I don't want you to feel like this is something completely new. What if we drew the region that we were rotating? Okay, so if we were trying to find the area of this region, we would have subtracted, well, we would have gone f of x minus g of x to get that area. So the same thing happens when we're trying to find that radius as well. So let's go ahead and find r of x here. So it is going to be f of x minus g of x. So f of x is 2 minus x squared. And then g of x is 1, so minus 1. And this is going to turn out to be 1 minus x squared. So here is our r of x. And now we can go ahead and find our volume. So volume is going to be pi r squared times height, so pi, and then the definite integral. Well, where are we going to go from here? Looks like we're going from negative 1 up to 1. Okay, of r of x, which is 1 minus x squared. And then we square it because that's part of our formula. And then dx. All right, and then our approximation here is going to be about 3.351 cubic units. All right, so the biggest thing here is draw what you're trying to get, draw your representative rectangle, identify the width and the radius. And you might have to be creative in finding the radius by subtracting some functions there. All right, in letter D, we have the function y equals the square root of x plus 5, the function x equals 5, which is right here, and the function y equals 5. And we want to revolve this around the line x equals 5, which is going to be right here. So it's going to revolve this way. And the area we're revolving is right here. So let's take a look at our representative rectangle. Okay, so we can see very easily this is going to be delta y for our width. And now what we need to do is find our radius as a function of y. So r of y. Now in this case, because our axis is off of the y-axis and it's over here, we're going to have to think a little bit differently. How can we get this value right here in terms of y? Well, the first thing we have to do is solve for x right here. Okay, so we would actually subtract 5 and then square both sides. So x is going to equal y minus 5 squared. Okay, so we know that this function right here is really y minus 5 squared. So that tells me that the distance from here to here is going to be y minus 5 squared. And I also know that the distance from here to here is going to equal 5, because that's the line x equals 5. And if we want to find r of y, it's just going to be the difference of the two. So r of y is really going to be 5 minus y minus 5 squared. Okay, so we can think we're going to take this whole 5, but then we're going to subtract the y minus 5 squared to get r of y. Now we also have to find our limits of integration here. And it looks like it's going to go from 5 up to right here. And I don't know what that y value is. So if we want to find this point right here, we know that happens when x equals 5. So y would equal the square root of 5 plus 5. So again, all we had to do was substitute x equals 5 in there. And so we know the height right here has to be the square root of 5 plus 5. And that becomes our limits of integration. So finding our volume, we have pi times the definite integral from 5 to the square root of 5 plus 5 of our r of y function, which is 5 minus y minus 5 squared, and then squared, because we have pi r squared, and with respect to y. And we'll go ahead and just plug that into our calculator. And our volume will be approximately 34.628 cubic units. Okay, so be very careful when we switch to a vertical axis of symmetry, especially one that is not the y-axis. You're really just going to have to think of how do I find that r of y, and that's going to be your biggest challenge here. Once you set up your integral, then your calculator can help you find the actual volume. Alright, so that is using the disk method to find a solid of rotation.